Hi everyone, this is Purma Mahalingam and you're welcome back to the video lecture series on field theory. So in last video lecture series, we have discussed about Maxwell's equations 1 and 2, which is for electric field and magnetic field. So today we are going to discuss about Faraday's law of Maxwell equation. That is the third law of Maxwell equations. Okay, come, let's go into the video. Here, what happens is first, Maxwell's equation. So Michael Faraday, who discovered the experiment that the current was induced in the conducting loop when magnetic flux link and the loop is changed. Magnetic flux links and the loop is changed. The current which is induced indicates that the existence of a voltage or an relationship between the induced EMF and the rate of change of flux linkage is known as Faraday's. So what is the Faraday's law? The Faraday's law is the current which is induced indicates the extensions of the voltage or an relationship between the induced EMF, relationship between the induced EMF and the rate of change of flux. The reduced EMF and the rate of change of flux is known as Faraday's law. In a closed path, the electric potential is developed due to the time variance, magnetic field in the vicinity of the closed path. The negative sign indicates the equations, indicates the Lenz's law. The negative sign indicates the equations in the Lenz's law. This states that the current induced in the loop in such a direction as to oppose the cause produced in this. So Faraday's law in integral form says that this in closed loop surface, electric field intensity with respect to line is equal to minus d by dt of surface integral. So magnetic flux density with respect to area. This is the integral form. Now coming to this integral form and explanation, here we can see what happens here. It is here what this represents comes here. Here comes what this represents is tell you to sum up the contribution of each position of the closed path, each position of the closed path. And C reminds the lines not the surface or which represents C represents the lines not in surface or volume integral. And E represents the electric field intensity. And this represents the dot product. This D represents the dot product. And what this represents the vector product, vector of particular field, and this represents what DL, this represents segment of the path, segment of the line. Say an incremental segment of the path C, that is line integral. Okay, and is equal to minus of d by dt, that is rate of change with respect to time. D by dt is rate of change with respect to time. And what this represents the rate of charge of the magnetic induction with respect to time. The rate of charge for the magnetic induction with respect to time. The magnetic flux into through any closed surface bounded by C. So this is magnetic for any closed surface with bounded by the C, that is nothing but line. Okay, this is what integral form. Now coming to the differential form. What is the differential form? In differential form, what happens is differential form reminds what happens. This is where the del operator. We know the del operator are nabla. So it remains the del in the vector form. Remains the del in the vector form. Previous we have seen in the curl form. Here what happens? It is in a vector form, and this is the cross product del operates in the curl form. Sorry, there is a curl vector. This is an curl vector form. The curl vector form remains the electric field in the vector. Electric field in the vector. Here comes the electric field. This E represents the electric field in V by M. And here, so what happens is the rate of change of magnetic induction with respect to the rate of change of magnetic induction with respect to time. This is what an differential form. Okay. Now, today's class, what we have seen is we have seen as what is Faraday's law and a definition for Faraday's law, and the Faraday's law in integral form and Faraday's law in differential form, the integral form. And the integral form, what happens is that the closed surface with respect to line integral is equal to change in time with respect to magnetic flux in density, magnetic flux density. In a differential form, what happens is this cross product, that is curl. The curl of electric field intensity is equal to minus of magnetic flux density with respect to time. So this is what today we have seen. And in the next class, we are going to discuss about the last Maxwell equation, Ampere's Maxwell's law. This is the last law of Maxwell equation. And this we can discuss in next class. Thank you so much for watching. Have a nice day.